On the edge of the cosmos, a black hole is supposed to swallow everything that wanders too close. The light vanishes, the clock for the fallen stops, and the void seems to win. Now imagine that same object not only swallowing light, but quietly leaking a whisper of energy back into the universe. That whisper is Hawking radiation, and it turns the darkness into a kind of glow. The strangest thing, this glow is not a bright beacon, but a trick of quantum physics happening at the edge of nothing. If a black hole can shine, what does that say about energy, about information, about what survives or vanishes when something crosses the horizon? The standard picture says nothing ever escapes its gravity well. Hawking showed that, at the quantum level, even the vacuum is a seething field of possibilities. The result is a glow so faint that sunlight would overwhelm it. Yet it carries a message. The universe never leaves a quiet corner untouched, because reality is tinkering with itself at the smallest scales. To understand why this remains one of physics' strangest bridges, we have to step back. For most of the 20th century, black holes were thought of as perfect cosmic vacuum cleaners, colossal, efficient, and utterly silent once nothing could escape. General relativity described them as regions where gravity is so strong that nothing, not even light, can climb back out. Quantum theory, by contrast, taught that empty space is never truly empty. Fields churn, particles appear and vanish in pairs, and energy can momentarily borrow a little from the vacuum if it repays it with interest. Before Hawking, the two ideas didn't meet. Black holes behaved like thermodynamic sinks in a purely gravitational sense, but the quantum side had no clear partner in the black hole story. Then came a simple question with enormous consequences. What happens to those vacuum fluctuations at the boundary of a black hole, the event horizon? Could the mysterious sea of creation and annihilation leak a little into the observable world? Stephen Hawking stepped into that question in the 1970s, using quantum field theory in curved spacetime. He treated the horizon not as a wall of stone, but as a delicate interface where radiation could originate. The universe, he showed, doesn't let the vacuum stay perfectly local near the horizon. Instead, pairs of particles and antiparticles pop into existence all the time. Usually, they annihilate each other almost instantly. But at the edge of a black hole, the horizon can separate the pair. One member of the pair falls inward, carrying negative energy from the viewpoint of an outside observer, while its partner escapes as real, detectable radiation. Energy is not created from nothing. The escaping particle carries away energy that effectively subtracts mass from the black hole itself. The process is exquisitely subtle, but it is universal. Any black hole with a boundary like an event horizon should radiate as if it were a hot object in the vacuum of space. To make this more tangible, picture the horizon as a wire of a dam that only allows one direction of flow. The quantum foam on either side is like a frothy river of virtual particles constantly spawning and dissolving. Most of these spawns disappear, but near the dam, a rare event can separate a pair long enough for one particle to be carried away downstream. The energy carried away by that escaping particle must come from somewhere. In the black hole's case, it comes from the gravitational well, the mass, the curvature, the energy that binds the whole together. Over time, this leakage drains the whole, albeit at a rate so minute for an ordinary stellar mass black hole that a clock would outpace the glow many trillions of times. The radiation is thermal in character, a spectrum akin to a blackbody, because the process is governed by the conditions at the horizon rather than by a particular atomic structure. The contemporary shorthand is that a black hole has a temperature inversely proportional to its mass. T, approximately 6 × 10⁻⁸ Kelvin times the sun's mass divided by the hole's mass. A solar mass black hole would glow at a temperature colder than the cosmic microwave background, effectively invisible by ordinary means. The core discovery did not merely add a new kind of light to the universe, it transplanted thermodynamics into a realm where gravity is supreme. Hawking's calculation also implied a deeply unsettling corollary. Black holes have entropy, a kind of disorder measure proportional to the area of their horizon, rather than their volume. It was as if the boundary itself stored information, and the evaporation process whispered that information might eventually be released in the radiation or encoded in subtle correlations. This link between gravity, quantum fields, and thermodynamics laid the groundwork for a whole program of research into quantum gravity, black hole thermodynamics, and the holographic idea that the universe might be described by information living on a boundary. The implications stretch beyond the math and the metaphors. First, the possibility that black holes emit radiation forces a rethink of their ultimate fate. An isolated black hole will slowly evaporate, shrinking as it loses mass and grows hotter in its last stages. For the big astrophysical black holes formed from stars, the lifetime is so immense that evaporation is practically inconceivable within the current age of the universe. But for hypothetical tiny primordial black holes, or for black holes formed in extreme early universe conditions, Hawking radiation could dominate their evolution, potentially yielding brief, dramatic bursts of energy as they vanish. The notion also sharpens the information paradox. If Hawking radiation is purely thermal, where does the information about everything that fell in go? Can it be encoded in correlations in the radiation, or is it lost forever? The debate has propelled ideas that tie gravity to quantum information, from the holographic principle to the modern interpretations of black hole complementarity and the speculative firewall debate. These conversations are not esoteric curiosities. They are a guide to what a future quantum theory of gravity might look like. In practical terms, Hawking radiation reshapes how we think about the universe's thermodynamic ledger. It suggests that even the strongest, most perfect absorbers can leak energy in a slow, inexorable drift toward equilibrium. It binds together the fate of a star's collapse with the physics of the early universe, and it hints at a cosmos where information is a fundamental currency, never quite gone, but perhaps redistributed in ways we are only beginning to comprehend. It also nudges us toward a deeper unity. The same principles that govern the behavior of a particle in a laboratory vacuum at room temperature are, in an extreme cosmic sense, at work at the edge of a black hole. The mystery is not merely that black holes shine, it is that the act of shining reveals the quiet, stubborn persistence of quantum reality inside gravity's grand architecture. And that message is still unfolding as physicists map the delicate border where space, time, and quantum fields intersect. We end where we began, with a question that keeps pulling us forward. What does it mean for something to be truly lost if a piece of it can echo back through a different form of energy? Hawking radiation does not give us all the answers, but it offers a compass. It tells us that the darkest objects in the universe are not truly silent. They whisper in a language we are only now learning to translate. If you want more journeys through these cosmic riddles, if you crave explanations that connect the smallest quanta to the largest galaxies, subscribe and come along for the ride.